So good afternoon, everyone. I'm James Koch, and I'll be presenting alongside Brian Espinoza on behalf of the Smart Morphing Wing Senior Design Team. And it's with our pleasure to present the design and analysis of Mattermorph 3, an experimental fully morphing UAV with camber-morphing wings and tail stabilizers. So before we begin, I would like to show you our team. We're a group of 15 undergraduate mechanical engineering researchers aspiring to contribute to the advancement of aerospace technology by means of developing and testing a fully morphing UAV. And in order to work as efficiently and effectively as possible, our team is structured into 3 sub-teams: the configuration team, the wing team, and the tail team. And each team is composed of 5 members, where one member is delegated the sub-team leader role, who has the responsibilities to help manage their own sub-team's tasks, as well as coordinate with the other team leaders. And in order to keep constant communication flowing from each member of our team, we utilize many forms of online communication, including bi-weekly Zoom meetings, Microsoft Teams for collaborative work, Discord for interpersonal communication, and Box for file sharing. And it's through these means of communication that we're able to complete every objective we set for ourselves, including first, designing a UAV that was capable of incorporating fully morphing wings and empennage. Second, designing proof of concepts for the wings and tail stabilizers that are capable of camber-morphing and non-stretchable skin. And lastly, manufacturing these concept models and performing actuation tests and wind tunnel testing. And we succeeded with our objectives by using a standard computer-aided development model. We first designed our components using CAD software and CAE techniques, including FEA, CFD, as well as topology optimization, before eventually moving on to our prototyping and testing stage, and eventually developing our completed product. And none of this would have been possible without our team's dedication to doing great engineering work, despite the circumstances of these unfortunate times, where we completed most of our manufacturing off campus in self-made home labs, as well as having various outdoor meetups to stay safe as possible. And it was through this dedication and hard work that we're able to complete many milestones over the course of the year, including, as previously mentioned, the full actuation and wind tunnel testing of our proof of concept models, developing an in-house MATLAB application for dimension sizing of XM3, finalizing our UAV design, and the many conferences we've attended and awards we've earned. And as for our budget, our team was allocated $3,200 to fund our project and research, where 22% of that was used for avionic equipment, 45% towards composites, 11% towards machine components, and 3% for 3D printing and miscellaneous items, which currently leaves us with $525 remaining, or 16% of our budget, roughly. So now you're probably wondering, what is a morphing wing in the first place? So first of all, morphing technology is a concept of incorporating various surfaces on an aircraft that are reconfigurable during flight. If you look at birds, for instance, you'll notice that they're able to adapt their wings to better suit flight conditions. For example, they're able to increase their span, which increases their lift, or swoop them back to become more aerodynamic. And having these morphing abilities makes them much more efficient animals. And currently, there's a lot of research trying to replicate these capabilities with the intent of making aircraft more efficient in the same sense. For example, the Bell X-5 was an experimental aircraft that utilized variable sweep morphing. And currently, an aerospace company known as Flexus is working on a flex foil, which is a type of camber morphing wing designed for fully sized aircraft. So which is very similar to our research in that our team is also experimenting with camber morphing. So a more accurate description of camber morphing is when the angle of the mean camber line is altered, which varies the amount of lift a wing can generate. And this allows the aircraft to maneuver similar to how an aileron or flap operates, except it uses a continuous surface and doesn't utilize a hinge joint. And having a smooth continuous surface greatly improves efficiency, which in turn can help reduce fuel consumption. But the most difficult aspect of any type of wing morphing is making a skin that can resist aerodynamic loads and be flexible enough for morphing. Current morphing research tends to focus on stretchable skins such as polystyrene foam or polyurethane rubber, which is very weak to aerodynamic forces and tends to wrinkle from protrusions of the internal structures, which in turn leads to inefficient aerodynamic surfaces. So we present Mattermorph 3. It's a fully morphing UAV that incorporates camber-morphing sleeveless control surfaces for the wings and tail. And we're solving this problem with the skin by using a laminate carbon fiber composite skin that connects to trailing edge slider mechanisms. And this effectively allows the skin to slide over the wing or tail, removing the need for the skin to be stretchable. This also provides rigidity against aerodynamic forces during flight and a smooth continuous surface for the air to flow over. And here's our innovative camber morphing design for the wing and tail. XM3 utilizes a laminate carbon fiber skin made of 2 plies of interwoven fabric that provide a rigid and smooth continuous surface. And our design also uses 3D printed skin supporting linkage mechanisms and trailing edge sliders to accommodate for the increase in surface area when cambering. And the skin attaches to the leading edge of the rib and the trailing edge sliders to allow the skin to translate freely, and linkage mechanisms are placed between each pair of ribs to prevent separation between the rib and skin during camber. And for the tail, a slightly different design was utilized, which involved trailing edge sliders that spanned the entire length of the trailing edge, as well as polyurethane foam sections, which acted as the linkage mechanisms in order to save weight. So the design for the ribs is an improved version of the very well-known fishbone active camber design. But in order to further improve the design, we replaced the corrugated structures with V-lines and I-beams, which help reduce buckling along the central axis. The actuation is then facilitated by a servomotor and a Carbitech CX6 ribbon, which runs through the rib and inserts into the trailing edge. And as you can see, again, the designs are very similar for the wing and tail. However, the tail rib utilizes a balsa leading edge to also further reduce weight. So here's a design for our fuselage. It utilizes a carbon fiber central boom as the main support structure for the wings and tail, and the main landing gear made of 16 plies of interwoven carbon fiber, which is then fastened between two 6061 T6 aluminum bulkheads. And as shown by the animation here, adjustable 3D printed ABS wing mounts made it possible for the wings to translate along the main boom, which allows the wing's position to be fine-tuned for the best location of the CG. And here's a diagram of the avionic components of XM3. It uses an all-electric propeller-driven UAV that incorporates a sunny sky brushless electric motor. It also utilizes two independent batteries, one to power the electric motor and the other to power the servomotors and auxiliary systems. And we're also utilizing a Pixhawk Cube 2 in unison with the GPS, as well as telemetry module to help gather data on flight characteristics, as well as our location. And here's a preliminary design and sizing application that we developed in MATLAB and used extensively during the design phase for XM3. The app implements multiple tools with a graphical interface and 3D display to help determine optimal flight-worthy parameters for the wing, the motor, empennage, as well as center of gravity. And the display updates in real time and allows the user to have a preliminary view of the UAV in order to intuitively assess the size of the aircraft. And I would really like to go more into detail about this application, but unfortunately, for the sake of time, we'll have to move on.
The analysis of XM3 began with the bulkheads. The main and front bulkhead designs were refined using a new analysis tool found in SOLIDWORKS Topology Optimization Studies. The figures depict the optimization evolution of the bulkheads. The goal was to reduce the weight by 30% while maximizing the stiffness to weight ratio. In each study, manufacturing constraints were applied such that the critical areas of the part were preserved. In the figure to the left, the area outlined in purple represents the preserved area needed to contour to the fuselage body. The central figure shows a mass reduction plot from the topology optimization study and illustrates which sections of the original shape could be removed for weight reduction. The figure on the right displays the final bulkhead shape, which passed all FEA static studies with an acceptable factor of safety. Static analysis was conducted on the carbon fiber landing gear frame to determine the number of plies that would guarantee a suitable factor of safety. A range of vertical landing speeds were considered, and a vertical load of 70 newtons was applied in a static study at the two ends of the main landing gear, where the wheels are attached. With the central part of the frame fixed as depicted by the figure, the applied loads resulted in a maximum displacement of 3.9 millimeters and a minimum factor of safety of 9.38. The mesh in all studies were refined until convergence was achieved. Motor analysis on the frame was conducted to ensure that the anticipated excitation frequency during takeoff and landing, estimated to be between 20 and 30 hertz, is far from the first natural frequency, and to check if the mold shape results in any twisting of the frame, which would require several plies to have a 45-degree fiber orientation angle during the layout process. A conservative approach was taken in the modal analysis by defining no fixtures. The first non-rigid body mode was a bending mode, shown in the animation on the left, and occurred at a frequency of 70 hertz. The second non-rigid body mode was a twisting mode, shown in the animation on the right, and it occurred around 170 hertz. Our analysis concluded that since resonance is unlikely to happen at this vibration mode, no plies with a 45-degree fiber rotation were necessary to implement into the landing gear. The stress analysis for the carbon fiber skin aimed to show that the skin was able to withstand the maximum expected aerodynamic loads during flight. For this reason, a pressure of 495 pascals was applied for the study. The shell of the model consisted of two 0.3 millimeter thick interwoven carbon fiber plies. The figures show the resulting maximum displacement and factor of safety. The maximum displacement had a value of 0.009 millimeters and a factor of safety of 146. The stress analysis for the main carbon fiber spar aimed to determine the minimum acceptable size that would be able to withstand the weight of the UAV. The model for the study had an outer diameter of 13 millimeters and was made up of 7 unidirectional carbon fiber plies with a stacking sequence of 00, 90, 90, 90, 00. The spar was fixed like a cantilever beam and had an applied weight of 5.66 kilograms, roughly half the weight of XM3. The results showed deflection of 5.6 millimeters at the tip of the wing with a factor of safety of 33, indicating that carbon fiber tube of this composition would be suitable. We purchased a tube from Rockwell's Composites that offers similar material properties. ANSYS Flint was used to carry out 2D static CFD simulations on the airfoils of both the wing and tail at different angles of camber. Each simulation had a flow domain of 7 meters in length by 4 meters in height. These dimensions were chosen to simulate a wind tunnel experiment, as well as the expected flight conditions, including the air properties at sea level. The inlet velocity remained constant at 20 meters per second. A triangular mesh was used with a 0.1 meter element size along the outer boundaries and approaches the sides of 0.005 meters along the outer surface of the airfoil. The table showed the results of our ANSYS studies when they converge. The NACA 4415 values are a reference against established values by NASA. For our studies, the max aerodynamic efficiency peaks at 5 degrees of camber with a value of 30.63. The camber-morphing wing and tail are the most novel ideas of our research. We built sample models of the wing and tail as a proof of concept. One difference from our initial design is that we use a fiberglass laminate instead of a carbon fiber for the skin because it was more readily available at the time. For the leading edge, we 3D printed a mold, which is how we were able to achieve the curvature as shown. The skin was bonded to the leading edge, the trailing edge, as well as the linkage mechanisms. For our test, we were able to achieve 15 degrees of camber without any aerodynamic loads applied. For the tail, a similar approach was taken to construct the sample model. However, instead of using balsa woods for the leading edge and trailing edge sliders, 3D printed ABS parts were used instead. As seen in the video, the ribs camber uniformly, trailing edge sliders translate into the slot smoothly with minimal resistance, and the skin remains smooth without wrinkling. We completed an actuation test for the wing model in the wind tunnel at school. For the test showed that the wing was capable of cambering with applied aerodynamic loads at speeds of 40 meters per second, and that the skin was resistive to these loads as well. Shown here is the expected flight path we plan to take with the help of our pilot at the Apollo airfield. The flight mission consists of performing a successful takeoff and landing, as well as having a flight time of 5 minutes. The main goal of this flight test is to demonstrate the effectiveness of camber-morphing. Next, I would like to highlight everything that the 5th cohort has accomplished. First, we placed second at the 2001 AIAA Student Conference, going up against schools such as Caltech and USC. We also placed second for the 10-minute presentation segment at the CSUNposium this year. We were also selected to represent CSUN's College of Engineering and Computer Science Department at this year's CSU statewide competition. Currently, we're in the process of finishing up the manufacturing of our UAV. We were able to manufacture one carbon fiber wing, however, it still needs to be cleaned up and sanded down before we can continue with the full assembly. As mentioned before, once the UAV is fully assembled, we will be performing the flight test. We also plan to submit our research paper for publication in a scientific journal. I would like to thank the 5th cohort of the Smart Morphing Senior Design team for their hard work and dedication to the project. Given all the current restrictions, we are extremely proud of the work we were able to accomplish. I would also like to thank our advisor on this project, Dr. Bichet, for his guidance during this school year. Thank you, and any questions?
I have a question. What benefits do you see with the morphing wing versus a traditional wing or a fixed wing?
So the main benefit of a camber morphing wing is that the skin is a continuous surface. If you take like an aileron from a traditional wing, you'll notice that it has that hinge joint, where it actuates. So by removing that, we can now have our skin be continuous, and the air will be able to flow over smoothly. We'll be able to maintain that boundary layer, so we can generate more lift effectively.
And then what does that translate into if I'm Delta Airlines and I want to buy a plane that has a fixed wing versus a morphing wing? What's the benefit to a commercial airliner?
Right. So I mean, if your wing is more efficient, then you're going to be able to reduce fuel consumption. So you'll be able to reduce costs and things like that.
So have you been able to estimate the fuel savings?
Unfortunately, no, we have not been able to do that estimation yet.
Is that a part of the competition? Is that like a criteria?
So our project isn't a competition. It's all research based.
Okay. All right. Thank you.
Yes. Thank you.
That's a good poke, though. Wow. And something worth considering. Is just as you guys get into it.
Right.
I did have a question about the wind tunnel results and like what data did y'all collect in the wind tunnel, and did you do any corroboration back to your analyses and things like that?
So the main purpose of our wind tunnel test was just to ensure that our model was able to camber during these subjected to these applied loads. We haven't collected any further data yet, but that's something we plan on doing.
Got it. So you weren't doing an aerodynamic study. You were just making sure you could actuate the camber.
Correct.
Right. I mean, unfortunately, our wind tunnel isn't fully functional yet, so we're not able to get that data yet. We would have liked to have that data, but so yes. So for this test specifically, it just served as an actuation test.
Right. Any other questions from the audience?
Well, did y'all show a top level schedule for when you're trying to fly and things like that? I don't know if I missed, or if you have some dates in mind. Just curious what kind of timeline this might be on.
So pretty much like our timeline right now is get everything done as soon as possible, and then so we can do our flight test as soon as possible as well. So we don't have an official schedule. It's been very difficult trying to manufacture everything outside of campus. So yeah, we're just trying to get everything done as quickly as we can and effectively as we can before we do our flight test.
I feel you. And you might even want to take a minute to sit down and look at dates, kind of like get your heads around how long it might take to do some things, and see like if you're headed towards something realistic, or if you're putting the right amount of work in the right area, like what your schedule critical items are, things like that.
Right. I agree with that. Yes, scheduling is always important.
I have a quick question. So you guys mentioned, so we were discussing about the materials that you selected for the wing itself, but what about the selection for the materials, for the rest of the airplane? So I mean, you're clearly selecting more expensive materials. So what's the reason for that?
Luis, do you think you could answer the question?
Yeah, hi. At least with regards to the fuselage, I know in the previous cohort, an issue with the fuselage was the rigidity of some of the structural components, and that is the reason why we chose, for example, the central boom to be carbon fiber, because our test pilot, for him, that was one of the main issues from the previous cohort, that his concern was that the structure itself was not stiff enough. So we opted to choose a carbon fiber boom, so that way the stiffness of the structure would not be of any issue.
All right, so we are pretty much, well, we're a little bit late, 1 minute, but we're good. So I'd like to thank the Smart Morphing Wing team for the presentation, and well, everybody else for their questions.
Thank you.